All right, so last time we didn't manage to finish an example, so let me go through the example before we continue. Here's the example. It says determine all three forms. All three forms of Fourier series. And the signal looks like this. This is t. This is x of t. 1, 2, 3, 4, minus 1. And the signal looks like this. So in this interval here, it is t squared, just t squared. Right, so what is it? It is kind of between -1 to 1, it's t squared, and then it repeats itself, because it's a periodic signal. So how do we do these kind of problems? There is as usually, what I try to do is kind of systematically give you a recipe that you need to follow in solving these standard problems. The first thing that you do before you even start working with your series coefficients, you say, what is the period? So what is the period?
2.
1 or 2? 1. Okay, so let's see. 1 from here. No, 2. 2. Period is 2. What is the fundamental frequency? 1 over period, which is 1/2. So that's the first thing that we need to determine. And then we start with our steps. Step 1 is always going to be calculation of A0. A0 is calculated as 1 over T0, integral over T0, x of t dt. But before you even calculate A0, what my advice is, look at the waveform and guess. What should be A0 here?
0.
What's the physical meaning of A0?
We have no
It's a DC component. Does this signal have a DC component?
No.
Are you sure? It's always positive. It has a DC component, right? Draw an average of this signal. Where is this average? Somewhere here, right?
Yeah.
Right?
Oh.
You see that? If I cut this and then I put them down here to build to kind of get an average value. So it's around 1/2, maybe slightly smaller than 1/2. That's what my gut feeling tells me, right? So then when you guess this, so let's say we say A0 guess, and I'm going to say, well, it's smaller than 1/2. That's my feeling, right? But it's always going to be positive. So let's then calculate it and see what we get. And what I get should kind of be reasonably in agreement with this. A lot of times you're going to be able just to look at it and say, oh, it's whatever value is. Sometimes you can. Most of the times you can't. But you can always ballpark it. We have a good feeling for what the average is. We're just really good in averaging. That's our, as humans, we're good in averaging. That's how we're built. So let's calculate A0 based on this formula. So I realize that, let me just say here, A0 is going to be 1 over period, which is 2, integral from -1 to 1, x of t, which is t squared dt. And you realize that this is 2 times integral from 0 to t, that's to 1, t squared dt. Why? On account of this being an even function, right? So integrating from here to here, the area under the curve is the same as from here to here. So this is t cubed over 3 from 0 to 1, so it's 1/3. So I'm claiming that the DC value of this signal is about 1/3. Is anything wrong with your gut feeling what it should be? No. So it's 1/3, right? But if I obtain here minus 2/3, you're gonna say no way, right? So, and then hopefully recalculate, right? So that's what I'm saying. Always guess before you calculate A0, because chances are your guess is gonna be pretty good. Now, step 2, we calculate AN. And AN formula, calculation formula, is 2 over T0, integral over T0, x of t cosine 2 pi n f0 t dt. In this case, this becomes 2 times 2 over T0, which is 2, integral from 0 to 1, t squared cosine 2 pi n f0 t dt. Let's see what are all these 2's. This 2 is the one, the same one from upstairs. This is T0, and this 2 here is coming from me integrating only over positive side, because the function is even, and therefore I can replace an integral in symmetrical border by 2 times integral on one side of the y-axis. Now we can do this different ways. To make story shorter, I'm using a table, integral table, that says something like this: integral of x squared cosine of ax dx is equal to 2x cosine of ax divided by a squared plus a squared x squared minus 2 over a cubed sine of ax plus c. And you know, it's complicated, but you can easily see the source of it. This is what you get if you integrate by parts 2 times, right? And this is what you would get here. You would integrate by parts 2 times. You would, you know, to knock down this polynomial in terms of t. All right, so if I apply this formula to this, I get that my an is going to be 2 times, and then let's just carefully apply it. This 2 times is from this guy here. Now, in this case, a is 2 pi nf0, so I'm going to have 2t cosine of 2 pi nf0t divided by 2 pi nf0 squared from 0 to 1. That's this first term, plus a squared, which is 2 pi n f0 squared times t squared minus 2 over 2 pi n f0 cubed sine 2 pi n f0 t evaluated from 0 to 1. Okay, the constant you don't need to put here, because you can put, for example, here c plus constant evaluated from 0 to 1. Constant at 1 is constant, minus constant at 0 is constant, so the constant always cancel each other, right? So the constant you don't have to, but these 2 terms you do. And then when you now substitute stuff, let's see. When I substitute here 1, now I should really substitute also what f0 is. Let me do that as well. And I apologize, I'm gonna put what f0 is in all of these equations to make the evaluation. So f0 is 1/2, right? 1/2, and then here also 1/2, and here 1/2. So when I substitute 1, I get the first term is going to be 2 times 1 cosine of, when I have 1 here and this 2 and 2 cancels, what is the cosine of n pi?
And minus 1?
Minus 1 to the n,
Yeah.
right?
Yes.
So this is minus 1 to the n. And downstairs, I'm going to have 2 and 2 cancels. So I'm going to have pi n squared. Okay? That's what I have for the first term. When I put in 0 here, then this t makes everything 0. Right? If I look at the second term, if I put 1 in here, okay, if I put 1 in here, really, just do this. Let's not worry about this for a moment. If I put 1 in here, then you have sine of n pi. What is the sine of n pi?
0.
0. So for the top, for the upper border is 0. When I put 0 in here, what's the sine of 0?
0.
0. So even though this is a mess here, this whole second term is 0, right? So this, didn't look like it, but it actually ends up having a really nice form of 4 times 0 to the minus 1 to the n over pi n squared. So that's my an term. And then step 3 is going to be calculation of the bn terms. Now bn, let me just put a definition here, is going to be 2 over t0, integral over t0, x of t times sine of 2 pi n f0 t dt. But we have noticed from the very beginning that there is something special about this function. What's special about this function? It has an even symmetry. So do I even need odd building blocks? No. So bn is equal to 0 for every n. For every n, since x of t is even. Okay? So believe it or not, we actually have our Fourier series here. X of t is equal to our DC component 1, 3, plus sum, when n goes from 1 to infinity, an, which is now minus, I can put 4 outside, minus 1 to the n, divided by pi n squared, times cosine 2 pi n f0 t, which is, I can say here, pi n. So that's our Fourier series associated with this waveform. Now that's form 1, the trigonometric waveform. As I say, from the computational standpoint, this is my favorite form, because I think this is the one that you're least likely to make mistakes. Everything is decoupled. And you just have to be kind of systematic and patient, not to mess up some calculations. But let's look at 2 other forms. B, that's our form where x of t is equal to, x of t is equal to c0 plus sum when n goes from 1 to infinity, cn cosine 2 pi n f0 t. So this is our plus theta n, right? This is our compact trigonometric form. But as we said, this one doesn't have its own calculation formula. You cannot calculate directly c or theta. You have to rely on calculations of a's and b's and then turn them into c's and thetas. And we know how we do that. C0 is equal to A0, therefore it's 1 over 3. Cn is going to be equal to square root of an squared plus bn squared. But in this case, bn is equal to 0. So what is Cn going to be?
An.
Be careful.
Plus minus a.
What is the square root of an squared?
Plus minus a.
No?
An.
No? Magnitude of an. Right? You probably, I'm sure some math teacher got you through this, on this in the past, right? Square root of x squared is equal to x, magnitude, positive value of x, right? Let's take a look. Square root of, let's say, minus 2 squared is what?
2.
It's 2, right? And it's not plus minus 2. Square root is a function, right? Function cannot have two outputs, right? We say the solution of x squared equal to, let's say, 2. Solution of this is plus minus square root of 2. That's a solution, right? And we have to say plus minus precisely because square root will always give you one value. Square root of 2 is square root of 2. Square root of 4 is 2. But the solution to this equation here is plus minus square root of the right-hand side. So in this case, Cn is going to be the magnitude of An. And what is theta n going to be? Well, theta n is going to be either 0 when your An is positive, or pi where An is negative. And when is An positive? Look at here. An is positive whenever n is even, right? So n even here. And n odd. Okay? So in this form, we need this. In this form here, x of t is going to be 1/3 plus sum when n is going from 1 to infinity. Always positive thing here. So it's going to be 4 over n pi quantity squared cosine 2 pi n, or I can just put pi n t plus n times pi. So when n is even, I'm going to be adding integers of 2 pi, which is essentially bringing you back to the 0. But when n is odd, I'm going to be adding pi, therefore putting a minus in front of it. Just like in the previous form. And then the last one, C, is now in this case x of t is equal to sum when n goes from minus infinity to plus infinity dn e to the j 2 pi n f0 t, which in our case becomes sum. Let me actually first calculate dn. dn is going to be equal as 1/2 an minus j bn. Since I already calculated an, I can put it in here. So it's 1/2, and an is given here. So it is 4 times minus 1 to the n over pi n quantity squared. And then bn is equal to 0, so I don't have to take bn into account. So this becomes minus 1 to the n times 2 over pi n quantity squared. And our series here becomes x of t is equal to sum when n goes from minus infinity to plus infinity minus 1 to the n times 2 over pi n squared e to the j pi n t. So this is our exponential form associated with this waveform here. Okay. Now, final check. Needs to be a lot of times, and I see this problem as being one of those. You have to be careful because what I always say is after you write this, then you have to see what happens for n equals 0. And for n equals 0, there is sometimes chance that this will not be a good fit. Because you can see here for 0, this doesn't work. It goes to infinity. So what you need to do is say when n is different than 0, and then plus 1/3. And now it becomes
So can we do it like that? 2 times 0 to infinity, and we keep multiply by 2 and plus 1/3.
I'm not following. Can we do
Minus
what?
infinity to plus infinity, we can write 2 times 1 to infinity, and
2
we
times
can
0.
add 0. 2 times 0 to infinity, and at n equal to 0, we have 1/3. Can we further simplify?
Okay, so here's what you can do. You can do, what I did here is I went from the first form into the third form. And then I did this conversion. And we remember we had the conversion where d0 was equal to a0, and dn was equal to 1/2 an minus j dn, right? So I have to do this conversion. Sometimes, you know, if the function is nicely behaved, you can actually put 0 and n equal 0 here, and nothing would nothing would go to infinity, it would fit. But in this case, you can't. You know, when you put n 0 here, it doesn't converge to n. So you have to kind of do what I just did. You know, input them both. Go ahead.
How do we determine n is not equals to 0?
Because
A of 0, that is the
Well,
first
look
zero.
at these conversion formulas. The conversion formula says if going from form 1 to form 3, then your d0 is equal to a0. For n equals 0, I'm making an exception. And for any other n, I can calculate it this way, right? But sometimes I don't have to do this exception because nothing special happens at a0. It just fits the formula, right? But in this case, I have to do that. Okay, so there you have it. So all three of them, there's really nothing complicated here, but it can get messy, right? And you fight messy two ways. First, you follow the process. You kind of go through these steps, and you really kind of know what you're doing, so that later when you look at your problem, you can go back and check individual spots, and you know exactly what you're doing in each individual spot. You're kind of neat and organized, and the second one is you do a lot of problems. That's always the best way to get the routine. You know, I can do this now, but believe me, I struggled just like everybody else, you know, when you introduce this first time. Because you forget the sign, you miss this, you miss that.
Depending on the XT, if the XT is symbolized with T squared, it's going to be easy one. If it's complicated, it's going to be.
The thing is, what is easy, what is complicated, you have to kind of, there are two things here that, and I'm telling you this because you're graduate students, you know. It's, math is never, if you can boil our problem down to math, it's solved, right? I mean, math at our level is very easy because we are not proving anything, right? We know that this series, this function has a Fourier series, and in our case, in engineering situations, when you use math, you're not worried about fringe things that math people, you know, worry about. You know, when does this converge? What is the convergence uniform? And those kind of things.
You just need to use it.
So conceptually, it's easy. It may get messy, right? And that's just the nature of things. So it's not difficult. It just it may be cumbersome, right? But conceptually, there's nothing difficult, and you just have to be patient, right? Sometimes some problems you can do in no time. Some problems takes a little bit longer, but conceptually, you're not going to run into anything where you say, okay, what do I do now? You know? And if worse comes to worse, you know, these integrals can already, you know, if I substitute here what f0 is, then I end up with integral of 2 times 0 to 1 t squared, the cosine of pi and t dt. And this is something that math lab would really happy to evaluate, right? Or even my calculator. I just plug in n, it will give me the value, and I can get the first 10 terms and be done in 15 minutes. All right, so that's an example. Let's continue with Fourier representation of the signal. So now that we have all of these components, we have them all as numbers. Commonly, we generate plots to show the spectral content of our signal. We call these plots Fourier spectrum, or Fourier's spectrum of a signal. There are two kinds of spectrum that you're going to find. One is called one-sided, and the other one is called double-sided. So let's define what those are and draw them for some cases. So Fourier spectrum. And the first one I'm going to talk about is one-sided. This one is generated from form 2. From form 2. Or as your books calls it, compact trigonometric form. The starting point here is the x of t is equal to c0 plus sum when n goes from 1 to infinity, cn cosine 2 pi n f0 t plus theta n. So we've done our work, we got our c's and we got our thetas, and we draw a following graph. Actually it's two graphs. On this axis is always frequency, and then on this axis is either your C coefficients, magnitude of them, or in this case just Cn, because C is always positive. And on this axis here is going to be theta n. And in the case of the periodic signal, what you realize is you're always going to have discrete spectral components. As we discussed the last time, the periodic signals are built out of sinusoidal components that have frequencies that are integer multiples of the fundamental frequency. So you can possibly have something at 0, something at f0, 2f0, 3f0, 4f0, 5f0, and so on, right? This is f0, 2f0, 3f0, 4, 5. Right? And what we do is we just put, whatever is the value associated with Cn. So this would be your C0, C1, C2, and so on. And then here you put whatever is the theta associated with the given component. This part here we call amplitude spectrum. And this one we call how? Phase spectrum. And this whole, these two together, we call one-sided spectrum. Each one of these components represents magnitude and phase of the sinusoidal, but you also have a frequency information for the sinusoidals as well. You have frequency of the sinusoidal is 2f0, its magnitude is c2, and its phase is equal to theta 2. So you have all of the information here representing a signal, right, in a visual manner. The other form that is also commonly used is called double-sided. This one is generated from form 3. In this form, you have your x of t given as sum when n goes from minus infinity to plus infinity dn e to the j 2 pi n f0 t. So that's the general form. Now, what we remember is that this dn is complex number, right? dn is a complex number. It came out as an evaluation of the complex integral. Therefore, in the general case, it is a complex number. And we can write this as sum when n goes from minus infinity to plus infinity, magnitude of dn, e to the j 2 pi n f0, or let me just do e to the j angle of dn, and then e to the j 2 pi n f0 t. Right, just writing the complex number into its form, the magnitude e to the j phase. Right? So if we approach it that way, then we can draw a similar charge to this one. But now, this is what we do. We say this is f, this is 0, f0, 2f0, 3f0, and so on. But also minus f0, minus 2f0. And here, we're going to draw magnitude of dn. So this is d0. This one is, let's say, magnitude of d1. But this is a magnitude of minus 1, d minus 1. Right? This becomes magnitude d2. This becomes magnitude of d minus 2, and so on. Analogously, we draw another axis here. This is f0, 2f0, 3f0, minus f0, minus 2f0. And you draw phase. Now, one thing, some things are you have to kind of know for these two when you're drawing this. The D0 is a DC component of the signal. Therefore, it's real. This is the same as A0. So the phase of D0 is always zero phase, right? It's constant. Now, the phase of D1, let's say D2 can be anything, right? Depending on the signal. But what you also know is that the phase has to be, if the signal is real, the phase has to be odd function of frequency. So if this is plus 3/4 of the pi, then this is minus 3/4 of the pi. So the amplitude spectrum has an even symmetry. The phase spectrum has odd symmetry, provided the signal that you're decomposing is a real signal. Okay, and this is where you draw dan. So this is again, we call this magnitude or amplitude spectrum. This is a phase spectrum. And the whole thing is double-sided Fourier spectrum of a signal. Okay? Both of these are used. They contain exactly the same information. If you know one, you know the other. There's no reason why you shouldn't be fluent in either one of them. Sometimes we're going to go to one-sided, sometimes we're going to go to double-sided, depending on the particular case. So let me go through a simple exercise here. This is the same as the exercise 6.4 in your textbook. It says, the two-sided spectrum of the signal is given in a figure. Determine expression for the trigonometric Fourier series. So you're given double-sided spectrum and asked to come up with a single-sided or form 2 of the Fourier series. So here's how the spectrum looked like. This is omega here, and this is the dn axis, and this is a 0, 3, 6, 9, minus 3, minus 6, minus 9. The value of this component here is 4. The value of this component is 3. The value of this one is 1. and the value of this one here is 2. And then I know that my magnitude spectrum has to be even function of the frequency. So I know that this has to be 3, this has to be 1, and this has to be 2. So that's a magnitude spectrum. The phase spectrum here, in this particular case, looks like this. The phase of the DC component has to be 0. This is 3, 6, 9, minus 3, minus 6, minus 9. And I'm given values here, minus pi over 6, minus pi over 4, minus 6, minus pi over 4, and minus pi over 2. And since this is a real signal, these need to be on the other side. So this is now pi over 6. This is pi over 4. This is pi over 2. Okay? So that's my angle of the n. So how do I write my trigonometric form? I can say x of t. What is my DC value here? 4 plus. Now, how do I determine the magnitude of this Cn here? Well, the magnitude, if you look at the last lecture, I went through and gave you the formulas for calculation formulas between different forms, and there you find that Cn is, let me see if I can point you. Okay, that's on a page 87. You have that the Cn, following the relationship, Cn is 2 times magnitude of dn, and the theta n is the same as the angle of dn. All right, so these are the conversion formulas. So in this case, I keep on writing. So it's 2 times magnitude of the first component, which is 3, and then I have cosine omega t, or cosine omega in this case is 3t, and then I put the phase, minus pi over 6. So that's the first component associated with these 2. Then I have the next one, 2 times 1 cosine 60 minus pi over 4. And then the third one plus 2 times 2 cosine of 9t minus pi over 2. So that's trigonometric form associated with the double-sided spectrum. So nothing really special. All right, so that's as far as the spectrum is concerned. There's another very important result here, and it's so important that it has a name, and we call it Parseval's theorem. Why is this result important to us? Because it gives us a relationship between spectral characteristics of the signal, its spectrum, and the power of the signal. You know, the power is always the king. You know, we always calculate something around the power, and it's important to be able to calculate the power of the signal. We know how to calculate the power of the signal when I'm given a signal, and especially in a case of the periodic signal, I have to square the signal and integrate over one period and divide by period. That's how I calculate it directly from the signal. But I would also like to be able to calculate it from the Fourier series itself. And first I'm going to show you how you do that, and then we'll have to discuss the very significant implication or very significant follow-up why it is beneficial to calculate power directly from the Fourier series.
Just to go back to 6-4, when you did this, the 2, 3 cosine, is that picking the positive values of omega?
Yeah, Yeah, picking the positive. If I were to pick negative values, then I would have to pick these negative phases. I can do negative also. I can say cosine of -3, but it would be plus pi over 6, which is exactly the same, right?
Right.
Because I can pull the minus, and since the cosine is even function, it doesn't matter, right? I could do this to answer your question. Let me just write it. So 4 stays 4, right? But I could say 2 times 3 cosine of -3, and then associated phase, pi over 6. And then plus 2 times 1 cosine -60 plus pi over 4, and then plus 2 times 2 cosine of -90 plus pi over 2. And you can see that these two are the same. Why? Because the cosine is even, so the fact that I have put minus here maybe is not, that's the same.
But wouldn't it be both of them combined? Both the negative and positive? It's only one?
No, because, okay, if you want to combine them, let's do that too. I can start by saying x of t is equal to 4 plus 3 times e to the j, j3t, j3t, or I should say, sorry, let me do it properly. 3 e to the j minus j pi over 6 e to the j 3t. So that's this component, right? And then I have to add plus 3 e to the j pi over 6 times e to the minus j 3t, right? Which is the, now, its counterpart on the other side. Now, I would do the same thing for the other one. So I would say plus, what is that I have? 1 e to the j minus j pi over 4, e to the j 60 plus 1 e to the j pi over 4, e to the minus j 60. And then the last one is plus 2 e to the minus j pi over 2, e to the j 9t, plus 2 e to the j pi over 2, e to the minus j 9t. So that's summing all of these components. Now, when you do this, you realize you can do this many different ways. The easiest way to say is I have a complex number plus its complex conjugate, so it's 2 times its real part. Right? So that's one way of doing it. The other, and then you get 4 plus 2 times the real part of this, which is going to be 3 times, cosine of 3t plus minus, that gives you directly this right away. Right? Another way to do this is to say this is 4 plus, and let's see how do I wiggle out of that one. So I'm going to say it's 3 times 2, and then I'm going to say this is e to the j 3t minus pi over 6 plus e to the minus j 3t minus pi over 6 divided by 2. Right? What did I do? I took 3 out and then put these 2 together and divided and multiplied by 2. And then you can see, it gives you, all 3 would give you the same. Right, as it should be, right? It's just a different way of view.
So we should use first one?
Use whichever one is correct.
You should
All
use the
3 of them are correct. The easiest one is the first one, right? But, whichever way you do it, you're all going to end up with the same result.
Sir, and when we are using any program like MATLAB, which will be more efficient? Which method will be more efficient?
I don't know. This is trivial. I don't. MATLAB. I don't know if you would have to write your own code. I don't think there is something that says give me the Fourier coefficients. You have to write your own code to do these increments. As far as I know, but I'm not positive. Okay, so let's look at Parseval's theorem. So Parseval's theorem. So here's the goal here. We have a signal x of t that is given as a0 plus sum when n goes from 1 to infinity, an cosine 2 pi and f0t plus bn sine 2 pi and f0t. So that's obviously our signal is periodic with a period t0 and all of that stuff. The power of the signal in a general case is defined as a limit when t goes to infinity, 1 over t, integral over t, magnitude of x of t, squared dt. You know that, right? This is how we define it. Now, if the signal is periodic, then essentially averaging over the infinite interval here is the same as the averaging over the period. So this reduces to a simple form where this is 1 over t0, integral over t0, x of t squared dt. Why? Because the average over one period is the same as the average over the entire t-axis. So the question that I have here is, can I calculate this power by knowing my a's and b's? And the way to find it out, well, let's put this in here, do the math, and see what happens, right? So substituting this into the spot of the x of t over there, we have px as integral 1 over t0, integral over t0, and then a0 plus sum, n goes from 1 to infinity, an cosine 2 pi n f0t plus bn sine over 2 pi n f0t, and then quantity squared dt. And by now you already sense, well, this is going to be the mess to evaluate, because I'm going to start squaring and there's going to be all sorts of things, and it will be, but a lot of things are like that. The things become really complicated and then they collapse in a second. So let me try to do this, and I'll try to economize the space. I trust that by now you can square and do the integrals, but I'm going to try to make this a little bit organized. So let's say I square it. So this becomes 1 over t0, integral over t0. And when I square it, I'm going to have, let me see here, I'm going to have this part squared, so it's going to be a0 squared, plus sum, n goes 1 to infinity, an cosine 2 pi n f0t, this part squared, plus the third guy squared, which is bn, sum bn, n goes from 1 to infinity, bn sine 2 pi n f0t. Now that's squared. So these are the first three terms. And then I have all the cross terms. So there's going to be three of these cross terms. First is going to be 2a0 sum, n goes from 1 to infinity, an cosine 2 pi n f0t. So that's the first times the second. And then I'm going to have first times the third, so it's going to be 2a0 sum when n goes from 1 to infinity, bn sine 2 pi n f0t. And then I'm gonna have a last one, which is 2 times sum when n goes from 1 to infinity, an cosine 2 pi n f0 t, and then times sum when n goes from 1 to infinity, bn sine of 2 pi m f0 t, and then I close the square bracket and put dt. So there are 6 integrals here to take care of, right? Each one of them, spelled out here. We should not lose the sight of what is it that we're doing. We're averaging over one period. So we're going to use that to our advantage because I know I'm averaging. If I know that the signal has a 0 average, I just get rid of it, right? So let's take a look at individual terms. I'm going to call the term I1, 1 over t, integral over t0, integral over t0, a0 squared dt. That's an average over constant over a period. What's the average of a constant? So it's just going to be a0, right? Squared. So this one is easy, right? Average integral 1 over t0, integral over t0, a0 squared dt. This is going to be a0 squared. Let's look at the next one. I2 is going to be 1 over 2 t0 integral over t0 okay, let me see how okay, well, let me skip a little bit. Let's just look at this one and this one. Well, let me just write them out first. So this is going to be sum when n goes from 1 to infinity, an cosine 2 pi n f0 t squared dt. I'm going to call that I2. I3 is going to be 1 over t0, integral over t0, sum when n goes from 1 to infinity, dn sine 2 pi n f0 t quantity squared dt. 4 is going to be 1 over t0, integral over t0. Then I can put a0 sum when n goes from 1 to infinity, an cosine 2 pi n f0 t dt. I5 is going to be 1 over t0, integral over t0. A0 sum when n goes from 1 to infinity, bn sine of 2 pi n f0 t dt. And the last one, I6, is going to be 1 over t0, integral over t0, sum when n goes from 1 to infinity, sum when m goes from 1 to infinity, an bm cosine 2 pi n f0 t times sine 2 pi m f0 t dt. So those are the 6 integrals that we need to take care of. This one we already took care of. It's a0. This one I can see that there's some work. This one there's some work. How about this one? What is the value of this guy? Well, what is it doing? It's taking the average of these. Well, you can see that the integration and summations are linear operator. They can change the order. So this integral can come inside. And this is really the average of a cosine. What is the average of the cosine? 0, right? So this one is 0. How about this one? 0 as well. So what we need to do is we need to do some work here, and we need to do some work in this one here. And let me do I2 first. So I2 becomes 1 over t0, integral over t0. And now I have another thing that I need to square. So this becomes sum when n goes from 1 through infinity, an squared, and then I have all of the cross terms, an squared cosine squared 2 pi and f0 t, and then plus 2 times sum when n is equal to 1 through infinity, sum n is equal to 1 through infinity, but n is different than n. And then an cosine 2 pi n f0 t times an cosine 2 pi n f0 t. And then I have to do dt. Right? Now, this splits into two integrals. The first one is this. Sum, when n goes from 1 through infinity, 1 over t0, integral over t0, an squared over 2, 1 plus cosine squared, 4 pi n f0 t dt. Do you see what I did? This cosine squared is 1 plus cosine of a double angle, and then divided by 2 here. This guy, the second one here, becomes 2 times sum n goes from 1 through infinity, sum n goes from 1 through infinity, n is different than m, an over 2, multiplying cosine of 2 pi n minus m f0 t plus cosine of 2 pi n plus m f0 t, and then that dt. Right? And there is somewhere integral here, right? So plus 2 over t0 integral over t0. Okay? Now, what is the average of this? Because that's what I'm doing, always keep in mind. Average of, there's no p squared here. Average of an squared over 2 is what? An squared over 2. So this, and what is the average of the cosine 4 pi n f0 t? 0. So this whole mess here ends up being very simple. Sum when n goes from 1 through infinity, an squared over 2. So let's take the second one. Bring this integral all the way here. And I'm averaging of this cosine. What's the average of this cosine? 0, right? Because n is different than n. This is always a cosine. What's the average of this cosine? So this whole mess is 0, right? So there it is. This is the I2. If you do the same calculations for I3, you get that this is sum n equal 1 through infinity bn squared over 2. All right, that's this guy. So we have everything calculated except for the last one, right? And let's just do the last one. Last one is I6 is equal to 1 over, let me just write it this way, sum when n goes from 1 through infinity, sum when m goes from 1 through infinity, an, and then integral of 1 over t0, integral over t0, and then sine, cosine times sine, and cosine times sine, let me just write it, and then, I don't know the trig identity, but let me just write this thing. Cosine 2 pi n f0 t times sine 2 pi m f0 t. And it really doesn't matter, because what you can remember is this. Cosine times sine is going to have two terms. One is going to be sum of the two frequencies, and the other one is going to be difference of the two frequencies, and both are going to be sines. So this will average sines over a period. So what is this term going to be? 0. It's going to be equal to 0. So that's the end of the derivation. Let me just write the final result. That says power of the signal is equal to a0 squared plus sum when n goes from 1 to infinity, an squared plus bn squared. Let me put them this way. Now, how beautiful this result. Now the question is, how do I remember this, right? Well, look at what we concluded. Look at this, and look at this. What I'm saying, what you should see is you should conclude is this. If I look at x of t, what is this? This is the power of a DC component, right? An squared over 2 is what? It's power of the n cosine component. And the bn squared over 2 is the power of the sine component. So it's almost like a magic. You see this power of the signal decomposes, the signal decomposes in sinusoidals, but they don't mix. You know, the aggregate power of the signal is equal to the sum of each individual sinusoidal that participates. This is a consequence of so-called orthogonality. Cosines are orthogonal to sines, and cosines are mutually orthogonal if they're of different frequencies, and the sines are mutually orthogonal if they're of different frequencies. So we have this beautiful result where the total power here is now decomposed into individual powers. And each one of these cosines that are part of the Fourier series, or sines, carries its own portion to the power. The total power is the sum of all individual powers. But not everybody contributes the same. In all examples that we did, you can check your notes and your homework problems, there is always n in the denominator of your an and bn coefficients. It's always downstairs. And what that means is, as the order of the component increases, its magnitude starts going down, and eventually it becomes so small that its contribution to the overall power is negligible. So this has a very significant implications for us. This means that if I can cut the Fourier series, what is really uncomfortable about this series is this infinity here. It says in order to represent a signal you need infinitely many components. But the saving grace is in this theorem here that says contribution of these components is proportional to their magnitudes, and you saw that in most cases the magnitudes decrease as n increases. Therefore, I can cut this and not go to infinity. I can go to some finite n if I'm willing to live with approximation of my signal. And I can actually be in complete control. If I want to capture, let's say, 99% of the power, this will give me how many components I need to keep, and I get rid of all the rest of them, knowing how much is the compromise that I'm making. We're going to come back to that, but let me give you the Parseval's theorem for all these three forms that we have introduced. So, the similar analysis, just like I did here for the form 1, can be done for all three forms, and this is the summary result. So, Parseval's summary. So, if I look at form 1, I have x of t is given as a0 plus sum when n goes from 1 to infinity, an cosine 2 pi n f0t plus bn sine of 2 pi n f0t. Well, the power of the signal in this case is going to be a0 squared, the power of the DC component, plus sum when n goes to infinity, 1 to infinity, an squared over 2 plus bn squared over 2. If I look at form 2, x of t in this case is represented as c0 plus sum when n goes from 1 to infinity, cn cosine 2 pi n f0t plus theta n. And in this case, the power of the signal is C0 squared plus some, n goes from 1 to infinity, Cn squared over 2, right? So look at how nice this is from our intuitive, feeling here. I have a whole bunch of sinusoidal. The total power is the sum of the powers in each individual sinusoid. And in form 3, you have that x of t is given as sum when n goes from minus infinity to plus infinity of dn e to the j 2 pi n f0 t. Here, the power of the signal is sum when n goes from minus infinity to plus infinity dn squared. So this is even nicer. It's shorter, but it doesn't have this nice intuitive interpretation as these do. Okay? All right, so I guess I'm going to stop here. And next time we're going to do an example of how you determine the bandwidth of the signal. So let me give you some homework problems. So problem here is 6.3-2-3-4-5-7-12. And then I guess 6.3-9, 3-10, 6.4-2, and 6.4-3. Okay, so some of them may actually require what I'm going to go over next time, but I don't want to do too many. Okay, that's it for today.